For centuries, physics has operated on a comforting premise. The universe is entirely predictable. If you understand the exact current state of a system, you can use strict mathematical laws to calculate exactly what it will do next. Down at the microscopic level, this predictability is governed by quantum mechanics, and specifically by a foundational rule known as unitarity. Unitarity dictates that physical information, the precise quantum state of particles making up an object, can never be truly destroyed. You can burn, crush, or scatter an object, but its data remains intact. This animation shows exactly what that means. If you track the trajectory and state of every single scattered particle, you can run the math backward to reconstruct the original shape perfectly, or fast forward to see where every piece will eventually end up. Because of this rigid mathematical rule, the universe effectively maintains an indestructible, eternal memory of everything that has ever existed. But when we zoom out to the macroscopic scale of stars and galaxies, a different set of rules takes over: the general theory of relativity. In this photograph is Albert Einstein, who in 1915 mapped exactly how massive objects warp the geometry of space and time, creating the pulling effect we experience as gravity. As we see in this image of a glowing accretion disk, his equations predicted environments of extreme gravitational warping, black holes. The gravity in these dark central voids is so intense that nothing, not light, matter, or even quantum information, can escape. Both quantum mechanics and general relativity work perfectly in their own independent domains, but force them to interact at the very edge of a black hole, and they create a mathematical contradiction that breaks our understanding of reality. In 1974, physicist Stephen Hawking bravely attempted to reconcile these two massive theories. He wanted to calculate how quantum mechanics operates at the intense boundary of a black hole. His mathematical models revealed something shocking. Black holes are not entirely black. Microscopic quantum effects at the horizon actually cause them to leak thermal energy. This diagram illustrates the process we now call Hawking radiation. Because the black hole is steadily emitting these waves of energy, it is slowly losing mass. Trillions of years of this steady evaporation will cause the black hole to completely vanish into nothingness, taking everything it ever swallowed with it. The fatal flaw lies in the specific nature of that evaporating energy. Hawking's calculations proved that this escaping radiation is entirely random. That means it carries absolutely zero usable data about the original stars, the swallowed planets, or the microscopic atoms that initially fell in to form the black hole. This side-by-side comparison highlights the disconnect. Structured data goes in, but only chaotic, formless static comes out. When the black hole finally disappears, the indestructible quantum memory of that swallowed matter appears to be permanently erased. Here is the ultimate dilemma. If the information is truly destroyed, the strict rules of quantum mechanics are broken. But if the information somehow survives and escapes, Einstein's theory of gravity is flawed. Theoretical physicists have spent decades proposing patches to resolve this mathematical crash. The most literal option is known as information loss. Accepting information loss means throwing out unitarity. We would have to completely rewrite the foundational math that allows us to understand atoms, molecules, and the microscopic world. Another hypothesis suggests black hole remnants. In this scenario, the evaporation process simply halts right before the black hole disappears entirely. But this leaves us with a microscopic, invisible fragment that somehow has to act as an infinite hard drive, storing the data of an entire star. Physically, the math struggles to support that extreme density. To avoid those dead ends, physicists turn to more radical attempts to save quantum mechanics, leading to the holographic principle. The theory suggests information never truly falls inside. Instead, it is flattened and encoded directly onto the black hole's boundary. As the black hole evaporates, this data is imprinted right back onto the Hawking radiation, allowing it to safely escape. But saving quantum mechanics this way creates a new issue, the firewall paradox. Forcing all that data to rapidly scramble and escape creates a violently energetic wall of particles right at the horizon. If a firewall exists, any object falling in would incinerate instantly. That violates Einstein's rule that free falling through a gravitational field should feel like drifting through smooth, empty space, so relativity remains broken. This ongoing collision between our two best descriptions of reality is actively tearing at our understanding of physics. Because no single patch cleanly resolves the math, the information paradox persists as the most critical unresolved wound in modern science. But contradictions like this are essential. Finding exactly where our current rules break is the only way humanity will eventually build a unified theory of quantum gravity.